Okay, so let us start the first topic of Unit 4, that is glacial processes and landforms. Now let us have a look at some statistics regarding the percentage of land area covered by glaciers at present and during the ice ages. So percentage of ice cover at present, this is about 10% of the total land surface area, and during the ice ages, that is around 18,000 years before present, it was approximately 30% of the total land surface area, or it was 16,000 BC. This is before present. And we know that there have been climatic variations since about 2 to 3 million years. In the history of Earth, there have been several glacial and interglacial periods in the recent history of the Earth. And let us directly come to the different types of glaciers. The glaciers are basically, they can be divided into two types that are unconstrained by topography, and those that are constrained by topography. Now these kind of glaciers, they are unconstrained by topography. What does it mean? So basically these comprise the ice sheets and ice caps. So we have two ice sheets, that is the Greenland in the northern hemisphere, Greenland ice sheet, and the Antarctic ice sheet. And ice caps, there are many ice caps on the planet. For example, ice caps are present in Iceland and in the Canadian islands, etc. Now these ice sheets and ice caps, these are unconstrained by topography. It means that the topographic slope does not control the flow of ice. Topographic slope does not control the flow of ice. Then what controls the flow of ice? It is basically in these kind of glaciers, which are unconstrained by topography, the ice sheets and ice caps. The topography does not control the flow of ice. Then what controls the flow of ice in these glaciers is the thickness of ice. This is what controls the flow of ice in ice sheets and ice caps. The difference between ice sheet and ice cap is just of size. These are smaller, these are larger. So ice sheets are larger, they are smaller, and there is no fine line of distinction, but approximately it is considered to be around 50,000 kilometer square. Means if it is greater than 50,000 kilometer square, it is ice sheet. Less than 50,000 is ice cap. Okay. So now let us come to the glaciers that are constrained by topography. Now these glaciers are the valley glaciers. Okay, the glaciers constrained by topography, it means that those glaciers that where the ice flow depends on the underlying ground surface or topography. Underlying topography dictates the ice flow. Here the thickness of the ice does not control the flow of ice. Rather, the topography or the undulations or the gradient of the ground surface or the topography or the relief controls the flow of ice. These are constrained by topography, so they are a different kind of glacier. These are usually found in mountain areas where the gradient of the land surface controls the flow of ice. Okay, then let us come to the factors controlling the occurrence of glaciers. Factors controlling the occurrence of glaciers. Now, there are many factors that control the occurrence: latitude, altitude, aspect, continentality. Now, latitude, altitude, aspect and continentality, all these control the temperature and precipitation regime. They control the temperature and precipitation regime of a region. So latitude governs temperature, altitude governs the temperature, slope aspect governs the temperature, and continentality governs the temperature. Similarly, it will also govern the precipitation. So these two variables, that is temperature and precipitation, obviously these two control the extent and thickness of snow cover, because ultimately it is the snow cover that will evolve into glacier. So this is controlled by temperature and precipitation. Now, apart from the temperature and precipitation, what else governs the extent and thickness of snow cover is topography. So here it is a separate factor that comes into the picture, and it will control the extent and thickness of snow cover. Finally, the extent and thickness of glaciers. So we can see the controlling factors in the occurrence and spread of glaciers is the factors are latitude, altitude, aspect, continentality, and topography. Now, it is easy to understand how latitude will control the glacier's thickness and extent, because you know that in the polar latitude it is very cold, and because of that cold environment there is more chances of snowfall, and then it will evolve into glacier. Similarly, high altitude regions have low temperature, they can evolve into they can have more snow. If there is enough moisture, then they can evolve into glaciers. Aspect is the slope aspect. For example, in the northern hemisphere, if you have a mountain like this and the sun is shining from south, this is south direction, this is north direction, and this mountain range is aligned east-west. This range is aligned east-west, so this is north and this should be west, and this should be east. Now, the sun will always shine from the south in the northern hemisphere. We are talking of the northern hemisphere. Sun will always shine from the south. So it will always lit up, or it will always warm the south facing slope. This is the south facing slope. This is the north facing, because this slope is facing the north direction. This slope is facing the south direction. So this will be heated up more, this will be heated up less. As you can see that this slope is having direct the insolation, the direct heat coming from the sun, and this will receive slanting heat or slanting rays, so there will be less heating. Over here you have more heating, here you have less heating. So this slope will have less temperature, this will have more temperature, higher temperature. So chances of formation of glaciers are more on this slope. This is known as this is how the slope aspect will control the temperature and the extent of snow, and finally the occurrence of glaciers. Continentality means how far or how close the region is to the sea. So if the region is very close to the sea, it will have a maritime climate, it will have more moisture, and if there is low temperature, then availability of moisture means more snowfall, more precipitation in the form of snowfall, more thicker snow, and have thick glaciers. And if at the same latitude, at the same altitude, with the same aspect conditions, if there are two regions having a continental location, that is interior location, one is having a maritime location, so the interior one will have less moisture because it is far away from the ocean, so it will have less precipitation, less snowfall, less snow cover, and thin glaciers or no glaciers at all. For example, in Siberia, although it is in latitude, it is equivalent to, you can say, many places in Canada, but you can see that in Canada, in the Canadian islands, we find glaciers, but in Siberia we don't find any glaciers. It is because it is far removed from the ocean. Anyway, now coming to the development of snow, or the development of ice from snow. So snow can be considered to be like a sediment. So this is equivalent to sediment. But you are all familiar with sediments and sedimentary rocks and metamorphic rocks. So the equivalence of snow is with sediment, because this is loose material, this is also loose material, and the density of snow is somewhere around 50 to 70 kilograms per meter cube. Then if the snow does not melt in 1 year and it persists into the second year, into the third year and fourth year and so on, it becomes compact, and then it evolves into firn. It is known as firn, where the density increases to about 400 kilograms per meter cube, and it is equivalent to rock, sedimentary rock, which is not too much compacted and lithified. Then firn evolves into neve. Here the density further increases, and this can be, and this is again analogous to sedimentary rock, but it is more compact. Within sedimentary rocks, we know that some sedimentary rocks are less compact, some are more. So the difference between firn and neve is just of compaction. This is having more compaction as compared to firn, and obviously it will have more density. And finally, the firn, when it becomes very old and it is compressed below fresh layers of snow and firn, then it develops into solid ice. And ice is analogous to metamorphic rock, because it is analogous to metamorphic rock, and the density is maybe somewhere around 800 to 900 kilograms per meter cube. Now ice, the process of formation of ice from firn or neve, this involves recrystallization, which is a metamorphic process. We know that metamorphic rocks formed by the recrystallization of sedimentary rock, the corners, they the, the, the contacts melt, and the material moves into the pore spaces, fills the pore spaces, and a metamorphic rock is generated. So we say it is recrystallized. Similarly, here also the this ice, fern or neve, at this stage there is just compaction. Compaction is involved, and beyond this stage recrystallization is involved into the conversion of ice. So basically, ice is basically a metamorphic rock. Snow is basically sediment, and fern or neve is comparable to sedimentary rocks. Now let us come to the types of glacial ice. Glacial ice is usually of two types: cold ice and warm ice. So cold ice is basically the ice that is below the pressure melting point, and this is close to the pressure melting point. So the melting temperature of ice at the surface is 0 degrees centigrade. This is the melting temperature, melting point at the surface of Earth. But the ice that is present at a greater depth, let us say in the ice sheet at 2 kilometers depth, the melting point at that depth will be lower, that is minus, let us say 1.6 degrees centigrade melting point at, let's say 2 kilometers depth. So at the base of the glacier, the temperature of the ice at the base of the glacier is important. So now at present let us discuss the cold and warm ice. Where it is situated, where it is located, I will discuss it later. So cold ice is that ice which is quite below the pressure melting point. So whether the ice is at the surface or whether it is at deeper level. So if we are talking of ice at let us say 2 kilometers depth, so it should be far less than 0.6 degrees. At least, let us say at least minus 10 degrees or minus 20 degrees. So this will be cold ice. Now based on the type of ice present in a glacier, the glaciers can be divided into two types. Now warm based glaciers, now here please focus on this word based. So it means that the glaciers which have a warm base, that means the basal ice is close to pressure melting point of ice. So this means that the ice is close to the pressure melting point, means that if there is a slight increase in temperature, there will be melt water, or you can say there will be water at the base of glacier. Water at the base of glacier. It does not mean that there will be rivers of water. It simply means that water, thin films of water. Films of water will develop between the glacier ice and the ground surface. So let us say this is the bedrock, here is the bedrock, and this is the ice. Between the ice and the bedrock, thin layer of water will develop. So this water will lubricate. It will basically lead to sliding of glacier. Now the base of the glacier is cold. then there will be no water, and there will be no sliding, and ice will be tightly bound to the bedrock. In case of cold based glaciers, ice is tightly bound to the bedrock, so there is a tight coupling between. Sliding will not take place. In old terminology, the warm based glaciers are also known as temperate glaciers, and cold based glaciers are also known as polar glaciers. But now it is known that it is not simply, the situation is not so simple that you have a glacier which is fully warm based and you have a glacier which is fully cold based, where the ice is below pressure melting point for the whole glacier. That is not the case. In reality, within the same glacier you can have different regions that are having cold and warm ice. Usually what happens is that in the upper portions of the glacier, in the upstream or in the upstream portions, you have cold ice, and in the downstream portion warm ice dominates. So in the upstream portion cold ice dominates and warm ice dominates. So here you have cold based conditions and here you have warm based conditions. Because in the downstream region of a glacier there will be higher temperature as compared to the upstream, because upstream will always be in a region where the temperature is low. If we talk of the alpine glaciers in the mountains, the higher elevations will be the places where the glaciers are originating. So obviously there will be low temperatures, and then we expect that the basal ice will be cold or below the pressure melting point, and the downstream portions of the glacier will always be at a lower elevation. Consequently, there will be the temperature regime will be less colder over here, and there are chances that the base of the glacier is having warm ice, or there is a warm based conditions may develop, which will assist in the movement of glacier by sliding. Now coming to the glacier balance, glacier budget or mass balance. Mass balance of a glacier. Now we will take the example of a valley glacier. So this is the mountain peak, that is the horn, and here we have the cirque. This is the longitudinal profile, long profile of a valley glacier. Now this is the ground surface. What I have drawn here is the ground surface, the bedrock surface on which the glacier ice is deposited. So starting from this point, which is the source, this is the cirque glacier, which I will discuss shortly. Cirque glacier, and here you have at some places there can be some undulations on the bedrock surface. So these will be reflected in the top of the glacier in the form of crevasses, and then this comes to end over here. Now this is the valley glacier, this is the cirque glacier. Obviously it doesn't matter whether it is the valley glacier or the cirque glacier because they are all interconnected. So what we have to focus over here is that there is a zone of accumulation and there is a zone of ablation. Usually the upstream portions are zone of accumulation, and the downstream portions are the zones of ablation. What does it mean? Here in the zone of accumulation, the rate of accumulation of snow. So snow accumulation is greater than snow loss. In this case it is reverse. Here snow accumulation is less than snow loss, but we have to consider it on an annual basis, means for the whole year. If you see for the winter season, then this zone of ablation, this lower portion will also have a snow accumulation greater than snow loss for the winters. But when you consider for the whole year, when you consider this balance, then you find that for this part the snow accumulation is less than snow loss, or losses are more than gains. Here the gains are more than the losses, and there must be some line, some dividing line between these two zones, and let us say it is somewhere here. This is known as the Fern line or equilibrium line. Beyond this line, the lower side, on the lower portion of this line, the losses are more than the gains of snow. On the upper side, gains are, on an annual basis, the gains are more than the losses. Now, from where the snow is accumulating, and what are the sources from which the snow is coming onto the surface of this glacier? One is the direct snowfall that is taking place from the atmosphere. The other sources is the avalanches from the valley walls, the snow that has accumulated on the sides of the valleys, just like snow is accumulated over here. So this snow will avalanche down the slopes and it will be deposited on the glacier. Similarly, on the sides, which we cannot see in this cross section, on the sides you have mountains, and on the mountains snow has accumulated. This snow will move down to the top of the glacier and will accumulate and become a part of the glacial ice. Losses, obviously, losses are by sublimation, by evaporation of meltwater, and by the loss of meltwater underground within the ice. Meltwater is lost because of. Now, one thing that has to be looked over here is that the glacial ice, the movement of glacial ice or movement of glacier, it may take place by internal deformation of ice, the glacial ice, or it may take place by the basal sliding of ice. It may also take place by the deformation of basal sediments, that is the sediments present beneath the ice. Now, this internal deformation of ice, this takes place by creep. This process is known as creep, and this takes place by the slippage within and between the ice crystals. So, the ice crystals, between the ice crystals and within the ice crystal, there is slippage. Fracture planes develop and ice deforms under its own weight. And basal sliding of the ice, obviously it depends on the presence of the water at the base of the glacier. So if it is a warm base glacier, it will have water at the base and sliding will take place, and if it is a cold base glacier, sliding will not take place. Deformation of basal sediments, the sediments that are present beneath the ice, these are saturated sediments, the deformation of the sediment will lead to the movement of the glacier. Now here what is important to consider is that the glacial ice, the basal portion of the basal part of the glacial ice is deforming. So this is, you can say, the zone of plastic flow or deformation. That is the creep. The creep is taking place over here in this part. And the upper part, this part is brittle ice. So this ice is not deforming. This will not deform, rather it will break. It is because it is brittle, it will break into fractures. So wherever there are irregularities on the bedrock surface, here and here, these irregularities will be reflected in the form of fractures on the top of the glacier. You can see here we have crevasses, here you have crevasses. Crevasses will be present only in the brittle ice. They cannot be present in the plastic ice, in this lower portion. And the ice in this lower portion is gradually moving downwards and finally outwards over here. Here usually we have the small thrust faults through which the basal ice emerges to the snout or the front portion of the glacier. The rate of movement of glacial ice. Now the rate of movement of glacial ice depends on ice thickness, obviously, and this point holds this. It is valid especially for ice sheets and ice caps, and it also depends on surface gradient. In the case of the glaciers, they are constrained by the topography, because if the bedrock surface is steep, the movement of ice will be faster, and the temperature of ice at the base. This is one of the most important deciding factors in the rate of movement of the glacier ice. As I have told you earlier that if the basal ice is close to pressure melting point, it will develop a thin film of water which will lubricate the base and sliding will take place. Sliding is a very fast phenomena as compared to creep. So rate of sliding is very, very higher or greater than the rate of creep. Creep is the process by which the glacier ice deforms. It is very slow, and sliding is relatively very fast. So the typical rates are, they may be 3 to 300 meters per year. So usually the creep, those glaciers that are dominated by the deformation that are dominated by creep, obviously they will be cold based glaciers. So they will have very low velocities, low deformation rates of 3 meters per year, close to 3 meters, or even lower, somewhat higher. But where sliding takes place, it can be up to 300 meters per year. It means within 2 or 3 years, the glacier ice could have moved about 1 kilometer. So this is a very, very important process, the sliding. And sliding depends on the temperature.